Hello, and thank you for joining us today. Today's webinar is Laser Ablation 102, the evolution of LA-ICP-MS through collaboration science, presented by Dr. Damon Green, Vice President of Technology and PLM Laser Ablation. We will be taking questions, so please feel free to submit the questions throughout the presentation using the question feature, and they will be addressed at the end. This webinar is being recorded and will be available for viewing within a couple of days. An email will be sent to you notifying you of that availability. Okay, now I'm going to turn it over to our presenter, Dr. Damon Green.
Thank you, and well, good morning, afternoon, or evening, depending where you are. Thank you for joining me for this presentation, and thank you to Lucas Smith for starting this series off last week with his basics of laser ablation. So hopefully this is a nice evolution of that particular presentation. So I'll start off just by explaining a little bit about who I am. Very quickly, beautiful picture up the top right before the barber shops closed down. I'm the guy who's responsible for the development of the photon machine systems within Teledyne. So I'm looking at existing technologies, new technologies, and specifically interested in the applications that are being used in the field, the developments that are undertaken in the field, to see where we can help out and develop them. My background, I'm a geologist. I have a geochemistry PhD in soft rock geochemistry, ICP-MS related. I've worked in trace metal labs at the Atomic Energy Authority. I've worked as an ICP-MS product specialist over the years. And for the last 17 years, I think over 17 years now, I've been working for laser ablation companies, so heavily involved in the world of laser ablation. A little bit about what we'll be talking through today, define what I mean by collaborative science, a very brief history of laser ablation, ICP-MS, 2 or 3 slides just showing where we came from and how we got here as a community. Then we'll focus on evolution of sample chamber designs, and it's quite critical because that leads to where we are today, directly linked to how we develop the Cobalt cell and why we developed the Cobalt cell. And that also links to the Iridia system, which I'll show a little bit about, and HDIP software. I won't be talking much about that today. I'll show you some images, such as the one we're showing on this slide, that have been generated by HDIP, but there'll be a follow-up webinar this time next week. One of my colleagues, Chiplin Stremtan, will be presenting on that software pack and showing about how data reduction has evolved. Also showed a few of the examples of elemental mapping, 2 or 3 at the end of the slide deck, and then some questions and answers. So what is collaborative science? I've tried to define it in italics there to say that it's essentially a commercial academic initiative. So it's a combination of commercial and academic, very important that both of those meet, designed to advance scientific understanding. So the science is the key. And on the right-hand side, there's some examples of key collaborative partners, and you won't be surprised to see at the top there a lot of very familiar names in the field of ICP-MS instrumentation, and below that some of the key institutes that we are currently working with to generate scientific understanding and hardware development. And they fall broadly into two groups. What I term to be funded research, where we physically pay cash to an organization to run a master's project, to sponsor a PhD project, fund research groups, workshops, conferences, and that kind of thing. So some of those are long-term, PhD project, 3 or 4 years. Some of them are much shorter term, a single workshop for a day, for example, or conference support over several days. In addition to that, we have what we call supporting kind collaborative research. That's something which evolves over time with a group of people. Typically, we're looking to develop close relationships related to specific applications, so we can understand how those applications are being developed, what the hardware and software needs are, and whether we're meeting those needs. We try to recognize as well, of course, the key academic labs. They're the experts. You guys are the experts in your field, not me, not the laser companies. We can help you, and obviously we're experts in laser technologies, but we need to understand from an application standpoint what is needed and not try and dictate to you what we feel is the right solution. And the other part of this is how we do this really is we're providing application and engineering support to help advance the science and understanding. So we can be looking at remote application help, how to develop applications, how to use the systems more effectively. And from an engineering standpoint, come up with new hardware options, new drawers, for example, for the sample chambers, or new bits of software that would allow you to do something which is currently not possible. So quite a wide-ranging definition of collaborative science. But what I want to show you is how we use those in the real world. Very brief history. You've probably seen these photos a number of times over the years. Laser ablation is a fairly mature technology. It's been around for a while. 35 years old if we take the 1985 Alan Gray setup from the University of Surrey. That's the setup you can see on the left-hand side there. A very basic beam delivery laser with a microscope. And then in 1987, Arrowsmith's paper showing the fundamental wavelength of laser ablating solids for elemental analysis. So fairly mature technology. It's been around a while. And when we look at the key development program of the laser products over the years, we've gone from what I say, relatively speaking, the first 15 years or so, 20 years or so, have been developments of lasers. Wavelengths of lasers have come down from the 1064 IR lasers down to where we are today, looking at 193s and femtosecond lasers. And in the later years, focus has been more on the applications themselves. How do we improve the applications? How do we develop the sample chambers to be more effective for particular applications? And how do we keep in touch with the ever-developing ICP world and ICP mass spec capabilities? When we look at sample chamber evolution, early sample chambers were very simple, gas-type boxes. We need a gas-type box. We place the sample in the gas-type box, we blast it with a laser, we generate an aerosol, and we blow that aerosol through on a stream of inert gas, typically argon and often helium. And there's some key advantages and disadvantages to that. The key advantage is that you can use a sample of various sizes. You've got a large space to put something in there. However, there's also some disadvantages. The poor gas flow dynamics being the key one. So that on the right-hand side there, I've taken an excerpt from a paper in the JAZ publication, and you can see that we're demonstrating that the gas flows within that sample chamber vary considerably depending where the sample is placed. Some of them will wash out relatively quickly, some will wash out over a long time, some get stuck in a little turbulent eddy and probably don't wash out at all. So typically tens of seconds of washout, sometimes over a minute. And you could, although you can use many different positions to put your samples in, you'll get different results, analytical results, depending where the sample is in the chamber. Now that's fit for purpose if you're looking at generic bulk analysis and you accept those drawbacks. For many, of course, that wasn't an option. And the group at ETH Zurich did a lot of work in the early days understanding the fundamentals of laser material interaction and indeed gas flow dynamics and sample chambers. And there's a lot of groups who have been involved in designing sample chambers over the years for specific needs. The one on the left there, the Niggle cell, the Merck Isotope Geochemistry Lab, Matt Horswood's group at BGS, put that design together specifically for a zircon puck. So there's several hundred zircons in that epoxy puck in the middle, taking some of the design principles from the ETH group, David Bleiner and Detlev Gunther's group, and pulled together that specifically for their application. And it works brilliantly. In fact, as far as I'm aware, I think Matt's still using that kind of design today. So for his application, it's ideal. However, one of the challenges when you start to use cells like that is that you are limited to just that one application and that one sample size. So there's been a work since, well, here's a paper from 2005, looking at how you can evolve 2-volume cells to try and maintain that analytical capability, but add the flexibility of a larger box, essentially, get more sample in or bigger sample in. And there's a few different ways of achieving that, different designs in the field even today. And on the left, you see what really is the initial Helix cell, the very first version of Helix cell from Steve Egan's group down at ANU. And this is, I suppose, the first real example of collaborative science. That group worked very closely with John Roy. John Roy, founder of Photon Machines, and John worked with these guys, took that cell, commercialized it with in full partnership with them, and we developed that capability. When we look at what we did with that chamber from that first design, this is essentially the current design. The internal cup volume has been modified over the years as we've worked with different groups and understood what the limitations are. It became an interchangeable cup. They put a lid on the cup at one point to try and improve the performance. And we ended up with a very flexible design that's very capable. Certainly limitations, every design has limitations, but iterative improvements to the design over the years mean that it's generally fit for purpose even today for a wide range of application types. When we look at performance metrics, and really this is what's important with any sample chamber, analytically does it work? We had a side project working with Professor Gerald's group, University of Arizona, looking to see how reproducible the data was across the sample chamber. And the reason we did this is because as the analytical science was improving and the analytical equipment was improving, we realized there were limitations in spatial reproducibility across the sample chamber. And George and his group flagged this for us. We worked with them and modified the design of mostly the sample draw, but a few minor design tweaks just to bring that up to spec. And they did this work for us. And again, we're back on track. This was probably 5 or 6 years ago now. And that led to what's essentially the Helix 2. And these are designs really that we can't initiate ourselves. We don't have the knowledge or the experience of the applications to be able to initiate these engineering designs. We need your feedback for it. So it leads to a question. Really, where we are now with sample chamber design is that everything seems to be getting faster. Largely that's been driven by elemental imaging applications, and those applications are specifically of interest because it means more business. It's a massive market. So as you can imagine, the ICP-MS manufacturers, the laser manufacturers are all keen to help out and work with that market space. But the question is, how fast do we need to go? And the answer is, well, it's application dependent. For some applications, you don't need fast at all. You probably still want hundreds of milliseconds because the long transient signals are probably needed, typically for low sensitivity applications where you want to generate as much material as possible over a period of time. But also when you're looking at the analytical system you're connecting to, if your ICP-MS requires several milliseconds of dwell time to take an analysis and generate sufficient counts per second, then it's no use having a system that generates a signal in 1 millisecond. You simply won't be able to measure anything of value. However, the 1 millisecond systems do have a value in that you can observe individual pulses. So whilst they may be too fast for the quad systems, there's certainly a value where you're looking at time of flight systems, or if you've got high enough sensitivity that you can generate meaningful counts per second in short time bursts. And the key point here is that you may want to observe those individual pulses for rapid elemental imaging. And that seems to be the area of rapid development at the moment. But the important point is flexibility. So with the Helix 2, for example, it's tunable. You can run that system from, I say, 20 milliseconds. Some have run them down below 10 milliseconds, but certainly typically up near 700 milliseconds. And that suits most applications. So the question is, how do we improve that performance further, particularly for imaging applications, without compromising the rest? The foundation really for the development of these systems over the years has been the geo market. That still is very much a key part of our business and something we wish to continue. So if we look at how we engineer the Cobalt cell, how did we get from the, how did we get from the Helix cell to this Cobalt cell? How do we manage that transition? And really it's through several transitions. Gen 1, Gen 2, bringing Gen 3. Oops, a daisy. It seemed to work too well. I apologize. But what I'm trying to show here, badly, is that there are several generations of sample device that have been evolved to get us a Cobalt. And it's through using a PhD project as the vehicle to do that. And we ran that through with Stijn van Malderen, a PhD student in Ghent. We ran through various iterations of this design, the tube cell design. And in 2016, we came to what's effectively the generation 6 of this project, which released the ARIS. The ARIS device, it's simply a fast injection connection really between a Helix cell and the torch, the back of the ICP torch. And the intention here is to maximize the capabilities of the helix cell, but using everything we've learned about development of tube cells. But while recognizing the tube cell wasn't a finished item and certainly wasn't commercial, we could take this device away, add it into the helix mix, and we're offering additional flexibility. So bringing that through to market allows us to start to help develop the applications and understand further what's needed for the faster development when we're going into the full tube cell style of development. So when we look at ARIS and what that brings to the market, what did ARIS actually enable? It really started off imaging in many ways. The fact that you could image with a standard 2-volume cell at 700 milliseconds was of interest. But once ARIS comes to the game, there's a few key papers came out. In 2017, Dave Chu and his group at Trinity College in Dublin presented this paper looking at zircon analysis. And on the right, box A, you're looking at a microscopy and slides looking at the zircon, its cathode luminescence image. You can see the growth bands in that zircon. And then the other 3 images there are looking at uranium, thorium-uranium ratios, and lead-uranium age. And the key is that by using this fast device, you're generating both faster data and more sensitive peaks, which means that you can acquire these image maps in less than 10 minutes. And you can run them faster if you wish, but in this case, this quality of image was absolutely fine for what Dave was trying to do. And they came up with the statement at the bottom there that there are a few reasons to perform spot analyses on complex polyphase zircons other than when sensitivity is needed. So in the opinion of Professor Chu's group, imaging of zircons gives you many advantages. And the paper is referenced there for those who want to follow up on it. But it allowed us to start to learn about these imaging applications. Additionally, working with the group in Thermo in Bremen, Chip Ryan and Grant Craig worked together with some of their colleagues there, you see listed at the bottom of the paper, attached the system to a multi-collector, really to see how much sensitivity can be gained by utilizing these highly efficient transfer devices. And the data here is showing what's essentially 4 times improvement. The paper talks about a doubling in sensitivity, and there's reasons for that. Really, that some of the numbers they were getting were frankly unbelievable, even though they were correct. But in order to get this paper published, they had to make sure that they doubled down on the claims they made. So doubling sensitivity. But even so, the fact remains that by using some of these high-speed, high-efficient transfer devices, there are significant analytical gains to be made. And this one surprised all of us, if I'm honest. We didn't expect to see this level of improvement in a multi-collector. There's many reasons why. Not all of them are fully understood. But generally speaking, it's a combination of more efficient transport, so more material is delivered per unit time to the plasma. And it's possible that there's actually more efficient ionization in the plasma because you're constraining those particles to the central core of that plasma. When we look through Cobalt cell and how it evolved beyond ARIS, what you can see on the left then is essentially it's the although we're calling that the Gen 7, 2017, it's the beginnings of devising a package for the Cobalt cell, devising a capability that you can actually package and use. So you have that 2017 Gen 7 testing the fundamentals of a tube cell and seeing how well that works and what condition it works. A lot of 3D printing involved, a lot of back and forth with our engineering group involved. And we boxed it up, as you can see below there. It's bolted onto the front of an Analyte G2 for testing to see what kind of analytical performance we can generate from that. On the right-hand side, that blue box, that's the beta version. There are 3 versions of that beta version in the field. One of them, University of Ghent, which is the one we photographed here. One of them was sitting in Toughwork in Thun, bolted onto the front of their system for testing on time-of-flight systems. And one of them was at the University of Vienna on an Analyte X site, generating bioimaging data in a real academic environment. And the intention being to learn what is possible, what works, what can we improve further. That paper listed at the bottom there was published just at the end of last month, 23rd of March. Really, that's the first paper that focuses solely on the sample chamber itself. So it's a paper describing the development and the use of that sample chamber as a beta sample chamber. When we look at some of the key questions to answer, one of them was about how important is the distance between the sample and the laser and the sample output in the tube cell itself. So that distance, you can see the red line there, it represents the focal point of the laser. And as we move along the sample with a varying surface geometry, we need to make sure that we're within a certain distance of the sample to maintain the analytical performance. And the question is, how important is that? Is it tens of microns? Is it hundreds of microns? So we've been working that through the academic institutions, come to the conclusion that actually it's important. It is important. We have a dynamic Z component in the system to take care of that. But you do have a little bit of leeway. You know, we're talking about tens of microns instead of hundreds of microns, certainly, but there's a little bit of leeway in how you generate the data. So we have a good understanding of how to optimize these systems. Of course, that's fast. So how do we slow it down? Well, slowing down a gas flow is relatively simple. The biggest question is not how to slow it down, but how to slow it down and generate robust analytical data. We don't compromise the data by slowing it down. We don't want to induce fractionation. We don't want to induce any bias in the data. So looking at how we do that, we start again with what we know, the helix cup. So the helix cup was re-engineered. We have this little lozenge module with a motor in it, the Z component there. So the interchangeable modules go to them depending on what application it's destined for. And in this case, the testing is certainly underway at the moment. We have a few beta Iridia systems in the field being tested for this particular application type, where we're looking to extend that into the several hundreds of milliseconds performance. So we're seeing that we can run this helix style long pulse module and generate hundreds of milliseconds of performance. And analytical testing, in fact, data I'm looking at just this week suggests that we're well on the way to signing that off, as well as analytically robust. So from an engineering perspective, relatively straightforward. Analytically, lots of testing and collaborative work needed to prove that it does what we say it's going to do. And that's how we tend to develop these systems. Looking at the sample draw, again, relatively straightforward, but the question is always, how do we make one draw do everything? And that's quite a challenge. So we've created a package here of various components that allow the user to configure the sample draw depending on the application of need. So you can have it for multiple slides, for POCs, as an open draw, lots of opportunity to do lots of different things with that space. Obviously, there's always limitations, and I guarantee there'll be some applications come up where this is inappropriate or not capable of their particular needs, in which case we want to learn about it. You know, I don't see that as a negative, I see it as a positive. I want to learn what it can't do, and we can engineer those solutions as well. So looking at the Cobalt cell evolution, we're actually at generation 9. So the product that is released, that is on the market as part of Iridia, is a generation 9 product, but that's the point where it's available for people to buy. Extensive field testing, as you can see, several years of development to get us here. And the key things that we've learned from the beta phase, 3 significant things. The third point is probably the least important, more about usability. The fact we've got moved the drawer to the front, it's easier to open and close the drawer with one hand. I say it's the least important. It's certainly relevant, and it's come from field testing. But having reversible gas flows, because ICP-MS systems sometimes run one side of the system, sometimes run the other. Depends where the torch is located, depends how the lab's laid out. So having it reversible was important. But the other key thing was looking at stage design and stage performance. Now, in the past, we've used stages which are external to the sample chamber. And they have to take quite a solid chunk of metal, a lot of weight to move around. And they've always been compromised as a result of that. We've never been able to use the stages we wanted to use because they needed to be robust enough to handle those weights. As we move to these systems, these high-speed systems, the stages now go inside the sample chamber. And we've got specific high-spec stages in there. But what we learned was that the stage spec doesn't equal performance. Initially, we were using a 20 nanometer spec stage, and they're brilliant in specs on paper, fantastic. But when you start to use them in anger, that isn't the performance you get in the real world. You load them up with a sample chamber draw with some samples, you're driving them around at speed, They work pretty well for a short period of time, but they're just not robust enough for day-to-day operation in labs. So we quickly recognized the need to improve that, and we came out with a different solution to the stages. But it's an important point. When you're looking at stage specs, the stage specs do not equal performance specs. What we need to be looking at here is actual day-to-day performance and reliability of those stages over time. There's some IP around this when putting this level of investment in. The University of Ghent have a patent on the tube cell design, for example. The dynamic Z, there's a patent in process for that, just to protect some engineering effort there. And of course, there's the two modules, the fast capability, sub-millisecond performance, and the long pulse for hundreds of milliseconds performance. And you can see how they're interchangeable at the top there. So when we go from the design to what it can do, how do we test this final design? Well, I mentioned we have a few in the field. And of course, the recent virus outbreak has slowed down some of the testing, indeed stopped the testing in some cases where the labs are now closed. The good news is some of these labs are now opening up a little now, so more testing is coming. But some preliminary testing, just looking at how we can optimize this. Again, the surprise here, we've got two plots here. The one on the left is from a gelatin sample, and the one on the right is from a zircon. And what you'd expect when you're looking at high-speed performance is that the softer material takes longer to generate the peak and be transported across. Normally, the expectation is that a soft material, the ablation parameters of the soft material, generally give you twice the performance of a hard material as far as transient peaks are concerned. We have to be careful of the language we use here as well. We're not talking about washout anymore. We're talking about complete peak and complete transient peak performance. Washout is half of this, of course. So you're looking at wash in and washout. And we do tend to use the word washout to describe this, but it isn't. It's a transient peak we're talking about. But what you're looking at here, again, depending on how you define that peak size, at the half max, you're 0.5 of a millisecond. At the 10%, you're at 0.9, and at the 1%, you're at 1.7. And that's comparable across both. That was the surprise, that they're both behaving very similar ablation parameters and transport parameters in this system. So that's very encouraging. So it leads to the development of the Iridia itself. It's a purpose-built laser ablation system designed for high-speed imaging. That's fundamentally why we did this. And it integrates the Cobalt cell. So we needed something to take that Cobalt cell and bring that to market, but it needs to be in a flexible pattern. So although it's designed for the high-speed imaging, we need to make sure that we can also run the geo samples and the standard quadrupole analyses that are required. So the first question, or the key question, for which laser to use? We don't make lasers, we don't own any laser designs. We buy lasers from companies as required and integrate them. And in some cases, we develop lasers with third parties, but generally speaking, we have the freedom to choose whatever laser we need. And we learned a few things. First of all the significant bioimaging publications to date have been on 193 lasers. Well, is that because there are no other types, or because that's the best lasers? So we looked around, we did some work with people to understand that. And what we found was that 193s are the preferred solution, and there's a number of reasons for that, and 3 of them are bulleted here. There's a smaller particle cloud generated with 193 lasers. And that means you also have a smaller range of particles there than the high wavelength lasers, so you get better analytical performance in the plasma, better transport efficiency, better ionization, and overall better analytical performance. The laser wavelength, we know, determines the amount of elemental fractionation. There's a lot of papers delving into the reasons for that and explaining that process. But fundamentally, we know that 193 is better than 213, is better than 266. And the final point I've made there is the analytical data is significantly improved using 193. And again, there's a number of papers explaining and running through the reasons why. The fundamental reason why we ended up with 193 is flexibility. The fact that most customers we're working with currently, very few of them are dedicated to one particular application. Even in the bio labs we're working with, some days they could be analyzing soft tissues, other days they're looking at teeth material or bone material. And having the flexibility to work with a variety of different sample types without compromising the analytical data we thought was most important. So 193 was selected. There's a page here, I'm not going to read through this. This is just the background to those claims. They're not my claims, they're the scientific community who've made those claims, and the papers that relate to those claims. I've listed them there. So as you learned at the beginning of this presentation, these slides will be available afterwards, and that's there for you to read through and check. So the Iridia development, looking at bioimaging, Jorge Piscinero's paper back in 2018 sums it up quite nicely. The ideal situation for bioanalysis is consecutive small square craters, flat bottoms, and no redeposition. So it's good reproducible ablation across the sample to get a known volume of material with each shot. And with 193, that's what we get. We have flat craters, we can run a range of spot sizes, options for the lasers themselves. To date, most laser on offer are in the order of 300 hertz, 1 to 300 hertz excimer, air-cooled. They can run at fairly high duty cycles, but fundamentally you can't run them flat out. If you try and run those 100% duty cycles all day, every day, they overheat and shut down. There are also 500 hertz options, and there's a kilohertz in test. So in order to move these forwards now to be appropriate for bioimaging applications, you need water cooling on them. And it's not true cooling, it's a chiller. It just stabilizes the temperature of the lasers, and you can actually run 500 hertz lasers now with 100% duty cycles for as long as you like. There's no real drop-off in performance. So there's a 300 hertz air-cooled for those who need the air-cooled. That can also be upgraded at relatively low cost in the field to a 500 hertz water-cooled option. And I mentioned there's a kilohertz in test. The laser itself isn't in test. The laser we know works, but what's in test is the analytical capabilities, because at some point we're going to start compromising either the plasma, the ionization capabilities of the plasma, or most likely the transport efficiencies as we run higher and higher rep rates. Higher rep rates means more material going through a fast system. We're trying to learn at the moment, where does it become saturated? So there's some testing going on there to understand how a kilohertz would operate. And fundamentally, kilohertz operation of a laser now is ahead of the ICP technology. We can run the lasers faster than we can analyze, and that's even true of time of flight systems currently. So it's nice to be in a position where we've got the choice. We're slightly ahead of the related technologies, but fundamentally, analytical gain is the key. So kilohertz is in test. It's available if you're interested, but it's not something we're promoting heavily at this time. We'll look at 193. One of the criticisms of 193 that's come through various channels has been that it's not able to run at low energies needed to generate robust analytical data of tissue samples, for example, on a glass slide. And the argument made is that it's too efficient at ablating and ablates everything. Well, the truth is, of course, all lasers at all wavelengths ablate everything if you put sufficient energy into it. And energy density is the key, really, to ablation. So you reach the ablation threshold of material. That ablation threshold changes depending on what laser type you're using and what the material is you're ablating. If we look at 193 specifically, for a glass slide to ablate, you need somewhere around 1.5 joules per centimeter squared, possibly down to 1. And for tissue ablations, it's typically around half that, typically less than 0.3. So we want to understand how we can fully ablate tissue without ablating glass. This paper, the JAS 2019 paper, highlighted at the bottom there by Thibaut, Stin, and Frank van Hacker group in Ghent, that's showing effectively how to do that. You know, on the top right there, you've got a kidney section. You can see the microscopic image of that in box A. In box B, you're looking at the silicon data, and we're talking there about sort of tens and hundreds of counts of silicon. And in bottom box, you're looking at calcium data. And the point being that we can ablate the material without taking any appreciable glass. So there's no component of glass analysis contaminating the tissue analysis. So we'll look at the laser itself. You know, the laser we've moved to, sorry for all the text and numbers on this slide. There's a few key takeaways. That laser design has improved considerably over the years, excimer lasers particularly. There's a lot of nonsense spoken about unreliability of excimers and the expense of maintaining excimers. They certainly were expensive and difficult to manage years ago, but over the years they've improved considerably. The key change was when we moved away from thyratron lasers to solid-state lasers. Thyratrons were consumable items. They were expensive. They required a back-to-base repair whenever they wore out, and they did wear out. Moving to solid-state lasers, that doesn't happen. The solid state switch is essentially no longer a consumable. And we now have a laser with a 2 billion shot guarantee. And indeed, 4 billion shots we believe is typical. And we have data to back this up if anyone's interested. It's a 4 billion shot is a typical life expectancy before the cavity itself needs any attention. And if we put that into some kind of context, if you're running a system at 500 hertz for a minute, and I've put the calculations there, so you can see over a year, if you were to run 500 hertz for 2 hours, for 2 years of operation, firing constantly for 2 hours a day, every day, all year, which in my experience is extreme for most labs today, but possible in the future, that would get you to 2 billion shots. But if you're looking at the reality, when you get to 2 billion shots, your energy levels will simply start to drop off. In fact, it's likely to be 4 billion shots. So the cavity refurb is something that's likely to be needed at various points in your operational history of running a laser, but it shouldn't be a prime concern. It shouldn't be something that stops you from working every few months. The resonator optics were the key issue. So where the laser generates the output, there's an optic set in there, and over time they get dirty. The way the laser operates is firing electrical pulses, electrical sparks essentially across some electrodes, and it generates dust, it generates contaminants onto the resonator optics. And typically we're expecting around 50 million shots on an optics pair. And we've now got that up to 500 million with data to prove it. And the 500 million is the specification on those optics. And in fact, data shows that a billion shots on optics is likely. So now you're looking at a system where the laser itself should no longer be a concern. If you run a standard service contract and have a preventative maintenance visit every year, there should be no issues at all with downtime on the lasers. Looking at the beam path itself, 193 light, well, it's quite aggressive. It's every time a laser is fired, every laser shot hitting a mirror degrades the surface of that mirror slightly. There's no way around that. You can minimize it. And the prime way to minimize it is to use a quality purge. So we've now designed a system with fully pressurized purge, mass flow controller, nitrogen in there. And the reason we use nitrogen, if you pass 193 in high energy densities through air, it actually ionizes the air and you generate ozone. And ozone is particularly aggressive and nasty on rubber seals, coatings on mirrors and so on. So having a purged, pressurized nitrogen system gives you better lifetime on the mirrors. Difficult to quantify, other than to say it is better, it improves the performance lifetime. But one thing we can quantify is the multi-use mirrors. So in the system, we have two key mirrors, nicely called M1 and M2, mirror 1, mirror 2. They're the first two mirrors the laser hits when it comes out of the laser cavity itself, the box itself. When they hit those first two mirrors, that's where they have the most energy, and that's where they do the most damage. And typically, this mirror set needs to be replaced, again, around 50 million shots, typically an annual PM. And what we found is that if we put these multi-use mirrors in there, instead of focusing in the center of the mirror, focus off to the side, and rotate that mirror through 4 or 5 different positions, and you get a fresh coating each time you rotate it. Something the user can do, and importantly, the way we set the system now, for all operation, alignment and maintenance, the thing is full class 1 safe. So you don't need any particular glasses on, you don't need to lock down the lab and go through all the usual laser safety to do an optimization of the system anymore in alignment. So looking through how we evolved to Iridia then, you've got a purpose design really for high-speed imaging, but importantly, not ignoring the geo. And with that in mind, we recognize that you want to do high-speed imaging, you need to be running high repetition rates. You're running high repetition rates, you want the laser to last for as long as possible. And these lasers like to run in a particular sweet spot. It's like driving a car. There's a particular rev range where your engine is most happy. If you're running it too low revs, it's juddery, it's stally. If you're running it too high revs, you're wearing the system out unnecessarily, wearing the engine out unnecessarily. It's exactly the same with lasers. There's a particular output for this laser where it's most happy, somewhere between 4 and 6 millijoules. And when you run the system at that level, it will go on and work to the specs I outlined in the earlier slide. However, that's too much energy for bioimaging. As I showed before, you need about 0.3 joules per centimeter squared for bioimaging. So we add in a second attenuator. So 2 attenuators gives you low energy for the bio applications, and a good stable output. At the extremes, what we're learning from some of the current collaborators is some of the materials they're ablating require such low energy that they're purposefully letting the gas go stale and letting the energy run down on the laser to achieve the best stability for the analytical data. That's not ideal for laser lifetime. It certainly solves the problem in the short term. So this gives you a stable, robust platform for low energy bioimaging applications. But similarly, recognizing the need for geoimaging and geoanalysis generally, some software controlled polarizers, and that second attenuator can simply be removed or not used to give you the higher energy and higher energy densities needed for the geomaterials. So really the Cobalt cell on the front end of this system were designed for flexibility and performance, but you're looking at single milliseconds to hundreds of milliseconds transient peaks. When we look at the laser specs themselves, 300 hertz air cooled, possibly upgradable to a 500 hertz water cooled if you wish. And to go from 300 hertz to 500 hertz, it simply requires a water cooler, water chiller being attached, and a bit of software from our side just to unlock that capability. But it's fundamentally the same laser. It's custom optimized laser for our design as well, our particular machine, to fit and work to the specs we need. And we guarantee 2 billion shots on that with a kilohertz laser in test, and analytical data from that will be bleeding out over the next year or two. Life expectation, around 10 times current industry standard. The other thing we've learned from most of these labs is they're not interested in playing with lasers, they just wanted to use it as a tool. So to try and generate a laser which is robust enough to be that device has been quite important. And at the bottom, the last bullet there is an integrated gas cabinet. Everything's in there, all the gases you need are inside the box. Looking at the application flexibility then, the dual attenuation we've mentioned to get you the low energy densities, down below 0.2 joules per centimeter squared, back down to 0.1 in fact we've been playing with, and the software control. And then at the sample chamber, there's also this EQC component in there, and that's simply an energy detector in the sample chamber itself. And it's surprising, but it's been a challenge for many years when running these systems to know exactly how much energy you're using. The software tells you what energy you've selected, but it's a calculated, calibrated reading based on an actual reading taken further back in the beam path. And when you start to run high repetition rate applications, of course, as I mentioned, you'll start to degrade some of the mirrors. It's nice to have confirmation that the system is purging well and generating all the optimum output all the way to the sample all the time. So we can measure that at the sample, in the sample chamber, under the same conditions that the sample is being analyzed. And I mentioned there's a demag option in there, simply taking feedback about the need for a full range of spot sizes. Still, we can't just focus down on the single microns, we still need hundreds of microns of spot size. So that gives us that capability. And then to finish off then, to bring us round to some of the applications. So I've got 3 slides just showing some of the applications and how we got from the Helix with Aris through to the Cobalt. And this data was generated on that beta Cobalt cell I showed. This was done at Ghent University. 3 images there. The top left image is a microscope image of the sample. The right image, top right image, is a stain of that sample, and on the bottom left is the analytical signal from zinc transposed over the top of those 2 images. So we can pull all those images together using HDIP software. You can probably just see the black line in that orangey image towards the top of the image. That's the 50 micron scale bar. One thing we've learned from doing this work, of course, is how sample prep is critical to the analysis of the biomaterials. And people far more specialized in this than I, again, for a good example, will happily explain how sample prep is critical to this kind of work. But we're looking at deparaffинized sections of mouse small intestine here. We're looking at 1 by 1 pixels. We've got spot size of a single micron, 150 hertz rep rate, and that took just over half an hour to acquire that data. But I mentioned sample prep. It's something of particular interest to me at the moment. In all of the data we're seeing on the bio work currently is done at room temperature. And the question I need to answer is, do we ever need a cryo chamber for this kind of analysis? To date, I don't think that's the case, but I'm always interested. So if any of you out there have any strong feelings on that or would like to get involved and work with us on that, I'll be open to those discussions. Looking at the geo, this is a nice zircon sample. Geological Institute in Romania, working with Ciprian Stremtan and some of his colleagues over there, Dr. Gabriel Sabao, he provided us with this sample to play with. 2 micron resolution, 300 hertz, 1 pulse per pixel. So each pixel was ablated once, and the imaging time was around 9 minutes to generate this image or this data. And because we're using a time of flight mass spec in this case, every pixel has within it all the data for all of the isotopes that were measurable, anything above background. We've selected in this image thorium and lead to really because they contrast so nicely in where they are spatially located within the mineral zone. But you can clearly see all the zonation in the mineral. You can clearly see where the lead has come in secondary phases through cracks and fissures in that mineral. And importantly as well, looking at images, it's important to recognize that you're looking at a pretty picture, certainly, but that pretty picture is real data. If the picture is high resolution and missing interferences, it's probably high quality data. If you're looking at a picture and you've got lots of interference lines around that picture, blurry bits, sections that are offset, it's probably because at that point that data is compromised somehow. The optimization of the system, maybe some interference between dwell times and repetition rates. There are plenty of papers discussing that as well. I'll be happy to share with you how to optimize the systems. But it's critically important. But the key takeaway is that whilst the picture looks pretty, you're looking at real data in this case. And then the final slide I'll show you. This is actually work that Cyprian will be presenting next week in his seminar, his webinar next week, looking at how we work with data, how we generate data output to make it usable in both image form and analytically from a calibration standpoint. Here we're looking at olivine phenocrysts in a bonanite sample, 5 micron resolution, less than 1 hour acquisition time. Again, a beta cobalt cell and using the TOFWork system in tune. And the image is on the right. You've got the iron image in the middle image there. Top right is calcium, bottom right is lead. And the image on the left is an overlay of those where we've combined them through HDIP software to give us a good visualization of where those elements are located within the sample. And again, Cyprian will run through those next week and explain how we get there and how valuable that is. So I hope that gives you some indication as to how we go about doing what we do. And we try not to be engineering led. We try to be science led. We don't always get that right, of course, but the intention is to work with key customers in the field, recognize labs where there's collaborative effort to generate good benefit for both parties. Some of those are funded, some of those are not funded, but any of you out there who have good ideas, good suggestions, feel there's a dead end that needs removing, a roadblock that needs removing, for example, technologically, that's what we want to hear about. That's how we develop these systems and how we bring them to market. And it's largely why it takes so long to get some of these things to market. And we can design a sample chamber in a matter of weeks. There's no point at all if it doesn't generate the good quality data. So that's why we do it, how we do it. And finally, just to promote next week with Cyprian and his dog, he'll be presenting Laser Ablation 201, looking at data reduction strategies and running through considerations for generating high quality image data. And with that, I'll come to the point at the end where we have questions. So thank you. I have a few questions in front of me here. I don't have time for too many, and we're running quite late, but I'll just run through a couple of these. One question was about the laser, the refurbishment of lasers when they come to the end of 2 billion or 4 billion shots. Typically, if you do a full refurbishment on a laser, the laser itself has to be sent back to the factory. That takes about 4 weeks, costs somewhere in the order of 10,000 euros to have that full refurbishment done. And you'd expect to do that once every few years, probably. However, with the new design of lasers, there is an option to do a cavity change out in the field. So the system can be down for a few hours only, maybe half a day, and the cavity is swapped out. That's significantly less expensive. And the cavities can be swapped out and refurbished 2 or 3 times before you need a full refurbishment. Another question was about collaborations. At the very beginning, I showed a slide with all the collaborative institutes, and the comment was that most of those appeared to be in Europe. There are 1 or 2 in America. There are very few in Asia at the moment. And the only reason for that is that, as you probably gathered by my accent, I'm based in Europe, I'm based in the UK. So I've been working over the years with a few key groups around Northern Europe, I'm certainly open to work with groups in China, groups in Asia more widely. If any of you are out there and interested, let me know. I'm very keen. I simply don't have the exposure yet from some of those regions to identify those labs and build those relationships. But it's on my list of things to do. And the final question was someone requesting a copy of the slide deck. And that will be made available to everybody who's on the call. If anyone has specific questions, please send them in, and we'll reply to those separately, either now or in the next few days. Feel free. Our contact details are all available as well, should you wish to get hold of us through the organisers. So with that, I say thank you very much, and leave you to the rest of your day.